So here we were introducing functions in class and talking a little bit about how functions are similar to machines where they do a single thing and they do it well. But notice in this model, there are a couple of ways that we can illustrate some things about functions. This one is a nice one that has a picture. And notice that these arrows all are going in one single line from an x value or part of the domain over to the y value or the range. And none of them, all of these have single arrows, and that's the main key, is that a single x has to be paired with a single y. So that's the first part in this bottom definition in your notes there. So if you take a look at these three models, we see that it gets a little bit confusing, but not too bad. Here the 72 is a little bit off center. It should have been down here a little bit because that red arrow is not pointing to it. But notice in part A here, this little a value is being mapped onto two different values, the 4 and the 16. So this would not be a function because of that. Uh, Part B, even though they're crisscrossing and everything, this is okay. And even the third one, where A and B are going to the same number, 72, that's okay as well, as long as there's just one arrow. By the way, I'd like to thank Mrs. M for these wonderful notes that I've pilfered from her. They're very organized. Looking at ordered pairs, that's another way to do this. So we want to make sure that there's a single number and it's paired up with a unique value on the other side. So what we don't want is we don't want to see another -2 or another 2. And in this case, we don't see that. They're all unique numbers, so this is definitely a yes. Over here, we've got a 3 that's being mapped onto two different values, and so that would be a no. That's not a function. Okay, and then the third case, it looks like all those numbers are okay. So there's another way to show if something is functional. Finally, we have the vertical line test. If we're looking at a two-dimensional graph like this one is, our Cartesian graph here has a line, and if you imagine vertical lines passing through your function, then they should only pass through one time, because right down here is your little x value, and that little x value should come out to a unique y value. And so letter A, that looks pretty good. Letter C, this looks pretty good. But notice in letter B over here, you can take a vertical line and pass it through here, and it will pass through two different places. And so that's the same thing as we saw with the ordered pairs. So of the three of these, this would be the big no, and the others would be yes. So in the notation, we have the name of the function, f. So we could have something like h of x. We could have h of t. But h is the name of the function, k of x, k of q, something like that. So k would be the name of the function there. The domain or the input is the one that's inside of here. So this would be your input value. So x, q, t. And then the function f of x value is going to be the range or what comes out, and that represents y. And remember, when we graph on the Cartesian plane, we have an x here and a y over here. The y is kind of representing the f of x in functions. So we oftentimes interchange those when we're talking about function notation. Okay, and then the value of f at x, or just f of x. So oftentimes we say that, or we say the function value. The function value at, see, the function. I like to put the word function. The function value at x. That's another way to say that. But all of those are just fine. Okay, so of course, just a quick review of what we did in Algebra 1. The x is the independent variable, also called the argument, and y is the dependent variable. So here we have an example of where y equals x squared plus 1. You could think of that as f of x equals x squared plus 1, just like they're showing there. And this would be written functionally, and this would be written in equation form, or explicit equation form. So we have two different forms here, as you can see, explicit and implicit. Look at the difference between the two of them. Simply, on the left, we have it written with variables on the left and a number on the right, or however we'd like to see that formed. On the right side, we have it solved for the y and then written in function notation afterwards. So that's an explicit definition there versus an implicit one. This one here is kind of neat. Yeah, this one here. So notice the difference between that because they've solved for y and then written it as f of x. I don't like the double equals, but that's okay. What we're really talking about is just this part right here. The function f is 9 over 2x. So again, functions are just like equations in many ways and have a lot of the properties that equations have. And what we're trying to do is look at what the different function values are at times. So f of 3 in this particular case with the function 2x squared plus 5. So simply plugged in, you can write equals, you can write the 2, put the 3 here. Don't forget about order of operations in this case. We're going to square the 3 first, make a 9. 2 times 9 plus 5. Okay, and we can do that all in our head. That's a 23. That one wasn't too hard. The second one is a little bit harder because of that negative. We get a 2. The negative 4 is going to be squared plus 5. And keep in mind that when we square the negative in the parentheses, we get now a positive 16. And so we get a 37. So I'm just doing that part in my head as well. And do a couple more of these here. Same function. So notice the 3x, though. That's a little bit funky. So that's going to be 2. And notice how I'm putting it into the parentheses here. Even though you don't see a parentheses around x, it's because of that order of operations. The 3x is all going to be squared. Now, we've talked about the father-grandfather rule before. There you go. So we're going to end up with this 9x squared plus 5, or 18x squared plus 5. So notice I do the multiplication after I have squared the 3x. That's a little bit tricky. Well, I guess I'm done, so I don't have to do any more there. I'll just box that. All right, looks great. Over here, f of negative x. So this is just to show what happens with these order of operations examples. That's going to be squared plus 5. And it's going to lend us some information here about what happens later on when we're talking about even or odd functions. So notice what happens when we plug that negative x in there for x. It just, the negative drops out. So we end up with 2x squared plus 5, or the same thing we started with, which is kind of interesting. And finally, we've got this one, f of x plus 3. So this time we're talking about plugging the whole thing in there. In that case, it's going to be 2. Once again, we're plugging that x plus 3 in for x, squaring it, and adding 5. Or in this case, further, x squared plus 6x plus 9, squaring that binomial, which of course we need to get real good at in these later chapters. So this can be then distributed with the 2 here. So we've got a 2x squared plus 12x plus 18 plus 5. Or final answer, and you could actually just, honestly, you can just box that guy. But 2x squared plus 12x plus 23 is really what they're looking for when they're looking for that function written out in ax squared plus bx plus c form. So now I'm going to have you pause the video and move on to the next part of the packet, which has the g of x function. I'll let you complete those 5 problems, and then I'll post them up in just a second. So go ahead and pause the video and work on those. All right, thanks for unpausing. Let's finish up. So we end up with this. This guy's going to come out to be 3, obviously negative 5, and then, whoopsie, sorry about that. Got to be a little bit careful when we work these things out. Minus, and this is a negative 5 squared. So lots of negatives in this problem. Negative 15 minus 25, or in this case, negative 40. So a very interesting problem there with the negative there. Sorry, I guess we're on the next slide. G of x plus 1. So here, again, parentheses certainly help us when we're putting an x plus 1 in there for x. X plus 1 here. I'm going to square it. Or 3x plus 3 distributed carefully minus. Now be careful here. This is a tricky one. I would square out that binomial x squared plus 2x plus 1, and then I would do the subtraction of it. So 3x plus 3 minus x squared minus 2x minus 1, or a final answer here, negative x squared plus x plus 2, as I bring together that 2x and the 3x and the 3 and the negative 1. And so I end up with an interesting problem here that gives us this. Okay, so that's kind of a nice one. There's another way to do this problem, by the way, and just let me show you here. Notice that the x plus 1 is common, so you could have actually written x plus 1 and then 3 minus x plus 1, like that. So in other words, we're taking out this common term, and then that would be x plus 1, and then this would be 3 minus x minus 1, or final answer here, x plus 1 and negative x plus 2. Now notice that that is actually the factorization of this dude over here. So that's kind of a fun problem to look at. All right, moving on. Here we're just showing that when we're dealing with function values, we're going to write g of x, which is actually 3x plus, let me start again, 3x minus x squared, plus g of 1, which is going to be, and again, I like to put this in a parentheses. We don't have to, but in this case, it's going to be 3 times 1 minus 1 squared, or 3x minus x squared. And of course, this is going to be 3 minus 1, or 2. Okay, so that would be the answer there. I should have probably put in equals and then worked on it here rather than directly underneath. Okay, one more time. So let's go ahead and put that equal sign the way we probably should do it. That's going to be g of negative x, or 3, again, negative x minus negative x squared. Very much like what happened when we did the first one with a negative number in there. This is going to be negative 3x minus x squared. Okay, so that's not too bad once you plug that negative in. Just pay attention to those negatives. And finally, what's the difference between that and putting a negative in front? Well, this is negative, and again, I use a parenthesis to say that the 3x minus x squared was the original g of x function, or negative 3x plus x squared. All right, something a little bit different in our answer form. All right, and finally, for this set, we're going to look at domains just a little bit. Domains are kind of, for functions, the way that things are for kitchen appliances. Like, you wouldn't put, say, a tin foil or metal in a microwave. Well, there's certain numbers you don't want to put in functions either. And there are a couple clues that we'll hit on as we go. In this case, the domain is going to be all real, so I'll write the domain is x, such that x is a member of the reals. So that's my little notation for, set notation for writing all reals. In the second problem, though, it's not hard to see that we don't want to have negatives under that radical. So we would want to make sure that the x value is going to be greater than or equal to 3 so that we can have positive or 0 underneath that radical. So here we would write the domain is x such that x is greater than or equal to 3. Now those radicals can get a little bit complicated depending on how big a power or whatever is underneath there. We'll see a lot of that stuff in the future. Here's another safety problem. We've got a 2x in the top, but in the bottom, we could factor that and see that's x plus 3 times x plus 2. And of course, when you see that, you realize that there are values of x that would make a 0 in the denominator. So we don't want to have zeros in our denominators. So in this case, negative 3 would be the culprit over here. Negative 2 would be the culprit over there. So I'll go ahead and state that in this case, the domain is x. Oh, that is a nasty looking brace, isn't it? Let me rewrite that. That's going to be x, the domain is x such that x is not equal to negative 3 or negative 2. Okay, so just to point out that the domain in this case is simply saying we cannot have zeros in denominators, and that's because of our contradiction of whether that goes to infinity or negative infinity, as I mentioned in class a couple days ago. So our last one over here, we have a 7 in the numerator. That's pretty harmless, but the denominator's got an x squared plus 1. And unfortunately, this is not factorable. I mean, you could say technically that x cannot equal I, because if we square I, we get negative 1, and negative 1 plus 1 is 0. But we don't talk about that. We're talking about real numbers here. So we would say the domain of this function is x such that x is a member of the reals. This is a very strange looking function because we think maybe there's something down there that won't work, but in essence, anything works just fine. All right, let's finish up this video with a couple of questions about a specific function. So if x is negative 1, what is the function value? So this is a plug and chug problem. So we put a negative 1, and we put a 2 times negative 1 minus 5, and we would just work that out. Negative 1 over negative 7, or answer 1/7. I think I did that correctly. The domain, so here we would want to write the domain, kind of making a mess of myself here, but that's okay. The number here, which would be the culprit in the denominator, would be, if you set that equal to 0, you'd get 2x is equal to 5. And we know that x, this is the number that x cannot be, so 5 halves. Okay, so we'd actually say that's the culprit, because if you put a 5 over 2 in there, you're going to get a 0 in the denominator. So x is not equal to 5 over 2. That would be our domain restriction. This one is kind of a cute little problem. F of x is 3. What is x? So in this case, we're going to take, and of course this is written improperly, right? This should be a k of x, but don't worry about it. It's fine. So k of x is 3. And what is x? So that's x over x, 2x plus 5. And, oh yeah, sorry. It's going to be 2x minus 5. That's what that was down there, 2x minus 5. Okay, looks great. Now all we have to do is multiply through by that denominator, or 3 times 2x minus 5 equals x, or 6x minus 15 equals x. 5x equals 15. That's bringing that x to the left side and the 15 to the right side. So x is equal to 3. So that's confusing because we said the function was 3, and look at that, the x value is also 3. So this is what's going on there. We've got a k of x function. Okay, here it is. It's in a thing. When we put the number 3 in, we get a number 3 out. How about that? Is the point 33 on the graph of k? You betcha. So just, yep, you betcha. X-intercepts and y-intercepts. So let's do the y-intercept first. Plug in 0. So plug in x equals 0. And then in the first part, let k of x equals 0. Okay, so that's the two parts that we're looking at here. So we'll do that in the first part, x-intercepts. We're going to get a 0 equals x over 2x minus 5. So the only way that can happen is if our numerator is 0. So in the first case, the x-intercepts are x-intercept is 0. And in the second, well, heck, if the x-intercept is 0, then the y-intercept has to be 0 as well. So there you go. Well, that concludes section 3.1. Once again, I'd like to thank Mrs. M for our slides, and I'll start with the 3.1, 3.2 wrap-up as my next video as we move our way through Chapter 3 in this Algebra 2 curriculum. Hope you enjoyed that.